Public-facing documentation for the IntentSim project often presents a labyrinth of metaphysical lore, referencing ancient seals and cosmic quarantines. However, the source code on the right reveals a different reality. The system operates as a rigorously constructed agent-based model, or ABM. An ABM is a computational simulation used to observe how the simultaneous interactions of multiple autonomous entities dictate the behavior of a complex system. This architecture translates abstract philosophical concepts into quantitative mathematical parameters. The concept of intent is defined in the code as a numerical vector that dictates movement along spatial gradients on a two-dimensional grid. A vector is a mathematical object that possesses both magnitude and direction. Emotional dissonance is measured as a precise mathematical rate of topological decay occurring within a defined computational network. To understand the architecture, we will track the math, from the individual agent vectors, through the spatial field mechanics, into the network's neurodevelopmental pruning, and finally to the machine learning prediction layer. This mathematical framework provides a structure for mapping cognitive philosophy onto a predictive model, allowing us to track how abstract states evolve into computable network data. The base layer of the simulation relies on a single interactive unit, the agent. Each agent functions as a complex probabilistic vector, moving beyond the static binary responses of traditional logic gates. This diagram isolates the agent vector's first core property. Intent is initialized using a normal distribution, creating a symmetrical bell-shaped curve. The second property, information content, utilizes a beta distribution to model data density, generating highly specific variance in how much data an agent carries. Finally, entropy calculates the degree of noise the agent introduces, while resonance state measures the agent's mathematical alignment with the broader system. When an agent is generated, the code samples values from each of these distributions. This creates a unique, mathematically distinct behavioral profile at initialization. The dynamic interaction of these finely tuned probability functions produces the high-level complexity seen throughout the simulation. Now imagine the scale. Thousands of these complex probabilistic vectors are released to interact simultaneously across the vast, bounded space of the simulation's two-dimensional grid. To manage these interactions, a KD tree spatial index partitions the space, mapping nearest neighbors. Once drawn, agents with matching intent variables exert a strong, calculated gravitational pull on one another. Next, the system calculates the field gradient by sampling coordinate values surrounding the agent on the x and y axes. Agents use this calculation to move toward the lowest local numerical point. A third force, phase-adjusted entropy, injects mathematical noise to prevent the agents from locking into static, immovable clusters. Every single movement is the strict algorithmic sum of three forces: neighbor attraction, field gradient descent, and statistical noise. The grid wraps around continuously. Agents crossing the eastern boundary re-enter from the west, preventing artificial clustering at the edges. This creates movement calculated as a transparent, frame-by-frame summation of topology, attraction, and noise. The simulation evaluates the health and stability of the entire agent swarm as a single entity. The primary macrometric for this evaluation is the Field Coherence Index, or FCI. The FCI is an aggregate score, measuring the alignment of intent variables across the entire network at a given millisecond. In a dissonance event, such as a sudden injection of conflicting variables, the network splinters and the FCI score drops sharply. Watch how the network recovers using the harmonic recovery rate equation. The first half calculates raw recovery speed, the change in FCI over time. The second half applies an exponential penalty based on dissonance amplitude, D. High dissonance flattens the curve. Finally, the lambda symbol acts as a damping factor. Researchers adjust to test the network's resistance. By combining recovery speed with an exponential dissonance penalty, the system successfully quantifies network resilience. The simulation's temporal dimension is designed to mirror the phases of human neurodevelopment. This timeline is defined as the harmonic Bloom cascade, characterized by distinct topological phase transitions. The Bloom phase is visible here. During this window, the system prioritizes rapid exploration, generating a massive volume of new connections between agents. This growth is followed by the pruning phase. The system reverses its behavior, halting strength toward that deletion line. Agents also carry a pruning sensitivity multiplier. Higher sensitivity values accelerate this decay, pushing the strength firmly below the threshold and completely snapping the edge between them. At the macro level, researchers can manipulate the over-pruning risk factor to test the system's structural integrity. High over-pruning risk factors cause the threshold line to rise, resulting in a fractured grid composed of isolated node clusters. The macroscopic shape of these evolved networks is dictated by these microscopic, mathematically defined edge deletion parameters. In the simulation's final layer, raw topological data is extracted to predict future system states. A random forest regressor analyzes macrometrics like spatial complexity and network energy. It is a machine learning algorithm that uses an ensemble of decision trees to predict numerical outcomes based on historical patterns. Training requires feature engineering, using the sliding lookback window shown here to format raw data into structured inputs. The window captures historical states from T-5 to T-1, forming the feature matrix X, which predicts the singular future state Y. These predicted macro trajectories are cross-referenced against a library of known neurodevelopmental patterns. This interface demonstrates the classification process. High structural volatility is mapped to an ADHD-like profile, while excessive edge pruning aligns with a schizophrenia-like profile. The ultimate utility of the engine is observing how adjusting a single initial agent variable results in a predictable macro network collapse. By stripping away the semantic wrappers, IntentSim proves that abstract philosophical states can be parameterized into predictive, phase-based network simulations.